a lot of times, you'd like to have this length information. Okay? So how do you separate if you want to know what the length of the products are? Anyone have any ideas? Right. Let's try a gel, right? Gel is always a good answer. So this is, sorry, it's 2. Okay, so in this case, we're going to basically do all the same things of the reaction, but at the end of the reaction, we're going to separate products on. So what kind of gel are we going to use for this? What kind of gels do you guys know about? Agarose, that's one. What's the other kind? Acrylamide, right? Those are the 2 types of gels. But that's not the right answer for my question, it turns out. Okay? Or they're both right, is one way to think about it. But I want to know about the length of my product. So if you look at that substrate up there, let's say I make a 100 base pair product and I make a 1,000 base pair product. And I separate them on the kind of gel most of you are probably used to looking at, which is a normal TBE or TAE agarose gel. Are they going to change a lot in how they migrate through that gel? Anybody know? They're not, actually. Okay? Because most of the mass of that product is the 5,000 base pair circle. Okay? So what do we need to do to look at the product only? What's that? PCR. Not PCR. PCR is the right answer for lots of things, but not for DNA synthesis, because you're using DNA synthesis to measure DNA synthesis, which is bad, right? So you're making new DNA to measure what you made.
Could you just use a higher percentage of water?
Nope. What if I denatured the DNA? Okay? What if I forced that new strand to come off of the 5,000 base pair product? Could I measure distances or lengths much better then? Right? So that's the key to using a gel. It has to be denaturing. So how do you denature? It's almost always a combination of heating, typically to around 95 degrees, just like for those of you who've done PCR, you always do this 95-degree denaturing step. Plus, the gel typically has either sodium hydroxide, which is if you're doing agarose, or urea if you're using acrylamide. And what these reagents do is, while they're not super terrific at causing things to come apart initially, that's what the heat is for, they're great at preventing separated DNA molecules from reannealing. Okay? So once you've heat denatured, if they're in either base or urea, then they cannot come back together and reanneal. Okay? So then you basically just separate these on a gel. So what is it going to look like? Okay? So I'm going to show you an image here. This is what you'd see if you're just looking at ethidium bromide. Okay? Everybody know what ethidium bromide is? Stains all nucleic acids. Okay? So this has nothing to do with what's labeled or not. This just shows all the DNA that's in those tubes. Okay? So the primer before you start the reaction is this little 25 base thing. Here's a 5,000 base template. They've come apart, so they run at very different positions on the gel, right? Everybody knows that you run from top to bottom. This is the plus electrode. This would be the minus electrode. Okay? Larger molecules move slow. Smaller molecules move fast. Okay? As you start to synthesize, you're going to incorporate nucleotides into new DNA, and this is going to separate, okay, so that at 30 seconds, you're going to see some synthesis, at 60 seconds more, 90, 120. Okay? So it's just steadily extending the length of those initial primers. Okay? Now this is looking at everything. And this is also a very efficient reaction. What I'll say is typically reactions don't use almost all the templates. So you can see here maybe 2/3 of the templates being used, so you can actually use ethidium bromide to look at this. But if we just detected either the radiation or the fluorescence, all we would see is these growing molecules. Okay? We don't see the primer. That wasn't labeled to begin with. we don't see the template. That wasn't labeled to begin with. We only see the new products. Okay? And this clearly gives us lots of additional information than our filter binding did, right? So we now know that the advantage of this is it gives us length information about our products. So if we just made 100 base pair products, if this polymerase never made anything longer than that, we'd see a very different profile than the one I showed there, where it just continually extends. Okay, so that would be information we could have based on that. The disadvantage is it's slower. Okay, running one of these gels, no matter whether it's acrylamide or agarose, you're talking about at least 20 minutes and as much as a couple hours, depending on the type of gel you run. Okay, and it's less quantitative. It's much more difficult to quantitate the bands in a gel than it is to quantitate sort of the amount of radioactivity generally incorporated into a template. Okay? You can get very, very accurate measure, for example, by radioactivity, but this is going to be a rough estimate. It'll give you an idea. And the one other thing I want to point out is that you'll note that as the products get longer, the intensity of the signal gets higher. Does everybody understand why that is? As you make longer products, you have more and more labeled nucleotides in your product. Okay? So that's fine in a lot of cases, but there are times when you don't want that. Yeah?
So is there anything preventing you from using both assays?
Not at all. You could split them in half. You could do one in one, one in the other. Okay? But it's just important you know the differences. Typically, that would probably be what you do as you evolved into more and more characterization of an enzyme, is you'd want to do both.